of neural network and deep learning, part 8. My name is TNB Ganesh, and we will start with this part 8. This presentation is based on material material from neural networks and deep learning, Professor Andrew Ng at Coursera. Hyperparameter tuning. This presentation will focus on hyperparameter tuning. There are several hyperparameters in deep learning networks, and we need to know how we can go about tuning these hyperparameters. Tuning deep learning networks can be both an art and a science. So let us look at the hyperparameters that we have basically in a deep learning network. We have seen in our presentations 2, 3, and 4 that we have the learning rate. We need to adjust the learning rate. Too big a learning rate can result in the gradient descent to actually overshoot the minima, and too small a learning rate can actually result in the gradient descent performing very slowly and going very slowly towards the minima. Then the number of activation units and number of hidden layers. These are two key parameters. We may think by increasing the number of hidden layers, our deep learning network will perform well. However, that is not the case. We need to be able to choose the appropriate size of the number of layers and also the number of activation units. Another parameter is the activation units itself. What is the activation unit we're going to use? What nonlinear functions are going to give us the performance we need? Is it going to be a tanh? It's going to be a ReLU, a sigmoid, a leaky ReLU, etc. And then the number of iterations. How long are we going to keep iterating to get the local minima? So the hyperparameters which are highlighted in red are the main hyperparameters. That is the learning rate, the number of hidden layers, the number of activation units, the type of activation units, and also the number of iterations. These are very key, and we have to focus on them first. And then additionally, we can actually do we can adjust if you're using the momentum method, we can adjust the beta value, which is typically in the range of 0.9. And lastly, we have if you want to do regression, if your neural network tends to overfit, then we may need to adjust the lambda parameter, regression parameter, or the key prop. Now we have so many hyperparameters, and how do we go about choosing an appropriate value? Is there a method to this, or should we just choose an ad hoc set of values and test it and then try another ad hoc set of values? So what Professor Andrew suggests is, for example, if you have the technique of brute force or brute force of grid search, where we have hyperparameter 1 and hyperparameter 2, and trying to do a grid search by taking all possible combinations of hyperparameter 1, hyperparameter 2, and trying to search for a performance will be very laborious, and also our progress will be very slow, because, for example, if we choose hyperparameter the learning rate alpha here, another hyperparameter beta, which is the momentum term, you may find that for a particular value of alpha, varying the value of beta may not result in a better performance. Rather, what he says is, we choose a random number for hyperparameter 1 and we choose another random number for hyperparameter 2, and then we take these random combinations and test, and that way we will converge to our local minimum much faster. And also we have to be able to choose the correct scale. How do we go about choosing the correct scale for different parameters? We cannot just choose a linear scale and choose values within that linear scale. So for example, for the number of hidden units and number of layers in your neural network, like for example, if we assume that the number of units per hidden layer, you would expect a value between 5 and 12, and number of layers in your deep learning network you want to be between 3 and 15, then we can choose a linear scale and choose a random number for hidden units between 5 and 12, and for the number of layers a random number between 3 and 15, and that will work. So we randomly choose a number between 3 and 15 for the number of layers, and number of for the hidden units we choose a random number between 5 and 12. For the learning rate alpha typically when you try to choose the value of the learning rate, we use either values 0.0, we start with some value 0.1, and then if you think it's not doing well, we may choose a value of 1, or we may choose a value 0.01. So it does not make much sense to choose a value between 1 3, 5 and 10. Typically it's on this power of 10 scale. So that is how we choose. And so what we can do is we can choose a logarithmic scale. So this is 10 power minus 4, this is 10 power minus 3, this is 10 power minus 2, this is 10 power minus 1, this is 10 power 0 and this is 10 power 1. So we choose a log scale and we choose a random number between minus 4 and 1, and then for to get the value of alpha we just compute 10 power the random number that we get, that is 10 power x. So this way, if we choose a random number between this and then raise it to the power of 10, we can choose a random value on the logarithmic scale for alpha, and that will help us to quickly localize into the area which to choose the appropriate value of alpha. Now for the momentum term, let's say the momentum beta is typically of the order of you'll be choosing 0.9, 0.99 or 0.999. So what we can do is we can choose 1 minus beta, which will be either 0.1, or for this value it will be 0.001, 01 or 0.001, which is essentially equal to 10 power minus 1, 10 power minus 2 or 10 power minus 3. So to get a value of beta, what we do is we choose a random value using any of the random functions in Python, R or Octave, and we get a value between minus 1 and minus 3, and then we compute 1 minus beta, which is 10 power x. So if we get, let us say, minus 2, we compute 10 power minus 2, which will be 0.001, and then to get beta we do hold on. We do 1 minus beta to get the value of beta. Beta is equal to 1 minus 10 power x. So that is what we do. And another technique is normalization, batch normalization. So we have seen that when we normalize the input features, that is we subtract from each of the input features the mean and divide it by the standard deviation, then our performance is much better. So the question is whether we need to be able to, we need to actually normalize the inputs to subsequent layers, because we can see A2 takes input from the previous hidden layer A1. So we could also normalize the inputs that come from the previous layer using the same technique of subtracting the mean and dividing by the standard deviation. So we could compute the linear activation as z minus the mean of the linear activation divided with the standard deviation. Alternatively, we could compute z tilde is equal to alpha of z prime plus delta, and by choosing the value of alpha and delta we can manage our normalization. So another point I wanted to mention was, let us say when we are using a combination of hyperparameters and we find 3 points here which let's say this point, this point, this point, where our performance is very good, then we can focus on this particular area, smaller subsection of this area, and then choose random values in that area. So, and finally, all that I have discussed in all these 8 parts is available and implemented in my book Deep Learning from First Principles, the second edition, vectorized Python, R and Octave, and you have this similar implementation in all the 3 languages, Python, R and Octave, and is available on Amazon. Thank you, and this ends the series of presentations on neural networks and deep learning. Thanks for listening.